Hi, my name is Chen. Today I'm going to talk about our work about binary search in secure computation. So this is a joint work with my advisor, Professor Marina Blanton from University at Buffalo. So first is the outline of this talk. So we will first review the background of the problem and also some existing solutions. Then we will go through our hierarchical solutions and also hybrid solutions. So first is the background. So I'd like to first talk about why the SMC is interesting. So we can imagine a scenario that some biomedical researchers want to conduct a research about some generic disorder, for example. So because they couldn't get enough data from the public database, so they may want to rescue some volunteers to collect their DNA information. But for sure, this won't be easy because no one would like to publish or reveal their own sensitive information. So SMC could be used to solve this problem because as a secure competition or secure multiparty competition is a technique that enables a set of parties to interact and compute a joint function of their private input, while revealing nothing but the final output. So it is, but actually, the problem of the secure competition is that it is not widely used for now. And I think one of the biggest barrier for applying the SMC in practice actually is the performance. So because almost every simple operation that's almost for free in the general competition will become very expensive, especially for the data access or data retrieval or data search operations. So why the SMC is so costly, or why the data access in SMC is so costly? So we can use a binary search example here. So here if we want to do a binary search, we may need to make multiple access and also comparisons to find the final target location. So the problem here is that how can we do this in a SMC scenario, or how can we do the binary search without leaking any information about the data? So actually the first thing we can do is to encryption. So we could encrypt or protect the data and also the input target by using the encryption or some other protection techniques. But actually this is not enough because we can still learn lots of information from the access pattern. So for example, we can see that our second access is in the right side of the array, which means that our target must be bigger than the median. So which is somehow like a set channel attack. So no matter what, the encryption itself is not enough. So in another word, the property we want to achieve actually is obliviousness. Which means that each operation should be independent from the data, such that no one can learn anything just from the program behavior or from the memory access pattern. So this is why some simple data access or data retrieval operation becomes very costly in the environment of the secure computation, because we need to mask or we need to hide everything to make sure no information can be leaked. Okay, so in a nutshell, in this work, we will explore and we will discuss about how to do the binary search in the secure competition. And we designed several solutions for the binary search problem with different properties and structures. And we further proposed a solution that could achieve a communication cost of square root of m, which is sublinear. So, and we also extend our binary search protocol to support the write operation, but we will not cover this part in today's presentation. So for the binary search problem, actually we assume that we have a sorted array, which is private, and also a private target value, which is denoted as B. So as we want to do is to find an element that has the smallest key that equal or small or bigger than the given target. So as we mentioned before, the key point here is how to hide the access pattern. So one existing solution is to use ORAM. So by using ORAM, the binary search could be done by invoking log times of ORAM access, which is similar to the idea of a normal binary search. But Actually, the problem is still performance. The binary search, the ORAM-based binary search is still costly, at least for the small to medium dataset, even after applying some known optimization designed for the binary search problem. So another existing solution is linear scan, which is also our starting point. So as shown in this example, the idea of the linear scan is that we do comparisons between the target value with all the elements to generate a tag array where the target location is 1 and all other places are 0. So after that, we can do a dot product between the target array and also the original array to take out the target element. So about the complexity of this linear scan solution, actually the good part of it is that it has a constant round complexity, but because it evokes linear times comparison, its communication cost is pretty high. So because this solution is just a linear scan instead of a binary search, so we should find some way to reduce the number of comparisons. So in our first solution, which is a hierarchical construction, so we first look at an example. So for this example, if we want to do a binary search, the first location we are going to touch actually is the mid one, the 7. It means that there's no need to hide the location, or there's no need to hide the information that we are accessing the 7. And in the second access, we will either touch the 1 or 17, which means that we won't touch anything else. So based on this observation, we could establish a structure like this. So we could say that because we only need to access one element in one layer during one access, so it means that when we are trying to hide the access pattern, we only need to hide which element we accessed in a specific layer instead of the entire array. So actually, we found that there's lots of interesting things we can do based on this structure. So we proposed two search protocols. One is tag-based, and another one is rotation-based. So the difference between these two solutions is how the access pattern is protected. So today we will only look at the tag-based solution because it has a better capacity. So then in the tag-based solution, we generate tags for each layer to select out the element we're going to access. So we start from the top layer. So we will do a comparison between the target array, between the target element with the element we're going to access. And based on the comparison results, we will be able to generate the tags for the next layer. And for example, here we are going to take out the 17. And once we take out this element, we can do another round of comparison and generate the tags for the next layer. So we will keep doing this until we reach the very bottom. So our tag-based solution has a much better communication cost because it only needs to do log times of comparison. But its round complexity is 5 log m because we need to do 5 rounds of communication for each layer. So no matter how many elements in that layer. So this gives us the idea that how we can improve its performance. The next is our hybrid solution. Our first hybrid solution, which is layer-based hybrid search. So here, actually, in the first, so the way how we improve it is that how we improve the performance of the tag-based solution is that we notice that there's only a small number of elements in the top several layers, but we still need to cost 5 rounds for each of them. So the round complexity actually is a bottleneck for the first several layers. It means that if we can combine the first several layers into a single array and using the comparison-based search to process this array, and sometimes later we switch back to the tag-based search for the rest layers. we should be able to save several rounds just from the top several layers. So from this table, we can see that the new hybrid search have a smaller round complexity compared with the tag-based solution. But if we look at the communication cost, we can see that all of them are still linearly depends on the input size of the size of the input array. So this is another problem we want to solve in our next solution. So in this solution, actually, we notice that when we do the search, we don't need to search directly on the entire array. Instead, we can first do a brief search to narrow down the range of the target. Here, actually, we notice that what we can do is we split the entire array into several subtrees or sub-arrays. So the target is located in the second subtree. So what we want to do is to select out the second subtree. So to do so, we first take out the last element in each sub-arrays or subtrees and do a search on this array. After this search, we will have a indicator array or tag array. And by using this tag array, we can easily select out or take out the subtree that the target element located in. After that, we will need to do another round of search to take out the target element. So the entire cost of this solution will be 2 rounds of search plus 1 round of dot product. Then let's look at the complexity of this solution more precisely. So because we assume that each subtree has alpha elements and we have beta subtrees in total. So because the first round search is performed on an array of size beta, so the cost for the first search will be big O of beta. And for the dot product, because its cost depends on the size of output, which is a subtree of size alpha. So the dot product's cost will be big O of alpha. And the second round of search is performed on an array of size alpha. So the cost for the second search will also be big O of alpha. So in total, the cost of the entire thing will be big O of alpha plus beta. And we know that alpha times beta is m. So it's easy to calculate the best setting is to let alpha be equal to beta be equal to square root of m. So by doing this, we could get a total communication cost, which is square root of m, which is linear. So in the performance comparison, we use 2 existing ORAM works and applied the optimization, which is designed for doing binary search. So from the plurs, we can see that the runtime of our subtree-based hybrid solution is better than all other solutions when the dataset size is smaller than 2 to 28 and 2 to 20. I mean, when the dataset size is smaller than 2 to 28 in the len setting and 2 to 30 in the win setting. For larger sizes, the runtime of our solution increases repeatedly just because the local work becomes the bottleneck. And finally, the ORAM solutions outperformed our solutions because they have a better computation and capacity. So in a nutshell, in this work, we explored the solutions for binary search in the secure computation scenario. So we proposed a suite of binary search protocols with different properties and structures. And also one of our hybrid solution that could lower the computing cost from big O of m to big O of square root of m, which is sublinear. Thank you.